All right. We're going to talk about calculations now in part 3, the final section, the final video here. We'll see that the actual math behind the calculations is not really challenging. It's just division in most cases. However, understanding what to put where is a bit of a challenge. So we'll go through several examples of that. In the first one, we'll talk about some probability that stems from my real life. In 2010, my wife was pregnant with twins. We chose not to find out the baby's sexes. The doctor told us that they were not identical. That is, you could have 2 girls, 2 boys, one of each. So let's review what those probabilities are. Oh, and also, so just if you need to know the difference between identical and non-identical, identical twins or monozygotic twins, the sperm, 1 egg, and then the egg splits in 2. Fraternal, 2 sperm, 2 eggs. So in the first case, when they both come from the same egg, they would be identical. Ours were in the second one, the dizygotic or the fraternal. So you can have all of these different combinations. They usually call the babies baby A and baby B. So for each of the babies, the probability that one is a boy is 50%. The probability that one is a girl is 50%. So that's the probability for both of these. However, that's not the probability of certain outcomes. Knowing that you have a 50% chance that the first one is a boy, 50% chance the second one is a boy, doesn't really tell you anything about the combination that you might expect. So what's the probability of getting 2 boys? What's the probability of getting 2 girls? What's the probability of getting 1 boy and 1 girl? So this usually trips people up. The most common outcome is 1 boy and 1 girl, and we'll see why that is in a second. So how do you get to 2 boys? Baby A would be a boy, baby B would be a boy also. 2 girls, baby A would be a girl, and baby B would be a girl. 1 of each, baby A is a girl, baby B is a boy, but it could also happen that baby A was a boy and baby B was a girl. So those are the 4 different outcomes. Boy, boy, there's 1 way to get that out of 4 different things that can happen. So the probability is 0.25. Boy, girl, girl, boy, 1 of each. 2 ways to get that. So the probability there is 2 divided by 4, 0.5. And then 2 girls. Both babies would have to be girls. And there the probability is again 1 over 4 or 0.25. So here the more common outcome would be having 1 of each. That's got the highest probability. Having 1 boy, 1 girl is equally likely. Okay, so what actually happened? Well, here's baby A.
Hey!
Paloma.
Right on.
And here's baby B. Lucia. All right, thank you, girls. All right, let's take a look at another example. This is an example from a research article that looked at how HIV status could potentially influence rental inquiries or responses to rental inquiries, willingness to rent a house or an apartment to somebody. So the authors here examined responses to rental inquiries. This was back when people would have to advertise things like this in the newspaper. So it wasn't uncommon for something to be rented and for the ad to remain for the rest of the week there. They called to see if the apartment was available, and they either mentioned they had HIV or did not mention that they had HIV. So the authors here were interested in whether HIV status affected that rental availability, reflected what the landlords were saying about the apartments, whether that caused an unwillingness to rent to people with HIV. All right, so a couple of ways to calculate things here. First, if we're interested in the probability of a rental being available overall, We can see we have a table here where it breaks it down when HIV is mentioned, HIV not mentioned. So the probability of a rental being available, that's going to be those two cells in this table, 56 and 76, where we had availability, over the total number of calls. So that would be 200 is the total number. So the probability that any one apartment was listed as available would be 0.66. So about 2/3 of them were noted as available overall. Probability not available, that's just in the numerator, 44 and 24, the two not available responses, again, over the total number of values. So the number of ways things happened over the total number of things that did happen. So 68 over 20, not surprisingly, that's 0.34, 0.66 and 0.34 are the only two outcomes, so they add to 100. Conditional probability. Conditional probability is, I think, the concept that trips the people up the most. The probability that something is available given that somebody has HIV. What that means is just look at the people who had HIV. Assuming that they had HIV, what was the probability that the apartment was available? And that there is 56 over the 100 people, or the 100 mentions of HIV, so 0.56. Now contrast this, the probability of HIV given that the apartment was available. That's saying, okay, just look at the apartments that are available. What's the probability that somebody had HIV, that it was the HIV person in that case? So 56 out of 56 over 76. So what's on the right side of that line really determines basically the denominator of this equation. If you think about the right side of that line saying, just look at those people who have that characteristic, that's probably a good way to get at it. With the independence rule, what we're going to ask is whether the probability of something being available was affected by HIV status. That is, were people more or less likely to be told the apartment was available if they had HIV? Well, to do that, we just compare the probability of available overall to the probability of available given that they had HIV. If the two numbers are the same, it means the events are independent. But what we see here is the numbers aren't the same. The events are not independent. And what that means is that people with HIV were told more often that the apartment was not available. So this study really provides some evidence of discrimination, at least at the time of the study, based on HIV status. All right, a couple of things to close out with. There are several ways to express probability. Probabilities are usually expressed as proportions. For example, a probability of 0.18. But they also might be presented as percentages. Expect something to happen 18% of the time. Chances out of 100, 18 out of chances out of 100 of something happening. We could express this as odds. 0.18 would be 1 out of 5.55 odds, as that's how you get to 18. So why should you care about this? Probabilities are going to be the foundation of what we call inferential statistics. And inferential statistics are really where all the action is in statistics. We're going to use probabilities to ask questions like, if the mean for a population is X, how likely is it to get a sample mean of Y? How likely would this sample result reflect a population that looked a certain way? When we get to hypothesis testing, z-test, t-test, ANOVA are all variants on questions of that nature. We'll look at questions such as, if the sample mean is Y, what can we expect the population mean to look like? We'll see ranges like this a good bit when we talk about things like political polls. We'll often see those polls reflected as with intervals or with a margin of error. And that's what that's getting at, trying to estimate what a population might look like given a sample. Another reason why probabilities are important is they actually relate to the normal distribution. The areas under the normal curve can be thought of as a probability. For example, we know that the proportion of scores of z greater than or equal to 1.5 is 0.0668. So we could also say the probability of a score being 1.5 standard deviations or more above the mean is 0.0668. It translates directly to a probability. All right, that's the end of this section.